SwayamPrabha. Digital India. Educated India.
Good morning. I'll continue the discussion on cascade analysis. The contents of the lecture are the cascade nomenclature and terminology. Here I'll discuss both compressor and turbine cascades. Then I'll review the expression for lift and drag coefficients, or discuss on compressor cascade performance test results, and then cascade losses. I'll explain now about cascade nomenclature and terminology. I'll go slow here to make you understand. An aerofoil is built around a basic camber line. Thus, it is the skeleton of the aerofoil. Thus, the camber line could be a circular arc or a parabolic arc. And theta is called the camber angle, which is equal to theta 1 plus theta 2. I'll explain what is theta 1 and theta 2. And a thickness T is distributed over the camber line along with the leading edge and trailing edge circle that finally forms an aerofoil. What I have told here, I have explained through this schematic where I have developed an aerofoil. To initiate the work, I have first taken a line which is called the chord line. Chord line is the baseline on which the aerofoil will be created. After the chord line, I have taken the camber line, which could be a circular or a parabolic arc, and dotted line here is the camber line. Now you can appreciate theta 1 and theta 2 at the leading and trailing edge. Look here, I have further explained with this figure what is theta 1 and theta 2. This is my chord line and this is the camber line at the leading edge, center of the leading edge circle, where the chord line and camber line intersect. If you draw a tangent to the arc, that is to the camber line, the angle made by the tangent and the chord line is theta 1. Similarly, at the trailing edge, you would get theta 2. And if you draw a perpendicular to the tangent at the leading edge center, and similarly a perpendicular at the trailing edge center, then theta is the angle holds by these two perpendicular. So thus theta would be theta 1 plus theta 2. So after we'll created the camber line, we'll distribute the thickness T, thickness of the aerofoil around the camber line with the leading edge and trailing edge circle. Let's finally make the aerofoil. Now leading edge and trailing edge circle are the two small circles And the chord is the distance between the leading edge circle center and the trailing edge circle center. That is why chord is the approximate length of the aerofoil. Similarly, what is A and what is B? You see, B is the maximum departure of the camber line from the chord line, and he is the location where that maximum departure occurs. And A is measured from the leading edge center. Thus, for a circular arc, theta 1 must be equal to theta 2 is equal to theta by 2, and A by C is equal to 0.5. Similarly, for a parabolic arc, A by C would be less than is equal to 0.5. After discussion on development of aerofoil, I'll now discuss about a cascade geometry. Now, the specification of cascade geometry is the pitch chord ratio and stagger angle. Stagger angle is the setting of the blade. And what is pitch? Pitch is the spacing between two consecutive blades. Thus, I have indicated here S is the pitch and C is the chord. So pitch chord ratio is defined by the parameter H by C, while C by S is often referred as solidity. Now look, I have indicated both turbine and compressor cascades here. So I'll take first the compressor cascade. Now, if I consider the axial direction, okay, so the chord line here makes an angle lambda with the axial direction, and lambda is called the stagger angle. So the stagger angle and the orientation of the blade defines the cascade, where pitch by pitch to chord ratio is an important parameter. Now, here lambda for the compressor cascade is considered as positive, while for the turbine cascade, you see I have indicated here lambda. However, the orientation of the blade will be completely opposite to the turbine cascade. If I draw the camber here, which I have drawn now by the blue line, and if you draw the camber for the compressor blade, you will appreciate the difference between the turbine and the compressor cascades, where lambda appears as same, right? Now, to make that turbine blades and the compressor blades orientation opposite, we often define as lambda as negative for a turbine blade, turbine cascades, sorry. However, another way to define the stagger is by the quantity beta star. Beta star is the angle made by the chord line with respect to tangential directions. Now, if we define stagger by beta star, then for compressor cascade, beta star will be always less than 90 degree. And for a turbine cascade, beta star will be greater than 90 degree. I have considered here few very important parameters like angle of incidence I, deviation del, and angle of attack alpha. To define that, I have considered aerofoil on the chord line. Furthermore, I have considered here the camber line also, which has been indicated by the dotted line. Now C1 be the inlet velocity, and C1 makes an angle I with respect to the camber line, so I is called the angle of incidence. Furthermore, theoretically, C2 should leave along the camber line. Now in this case, C2 makes an angle del with the camber line, which is called deviation. So C2 is deviating from the camber line. So I have defined now the deviation del. Now, what is angle of attack? Angle of attack is the angle between the vectorial mean velocity Cm and the chord line. So look, this is the chord line and this is the Cm. So this angle is nothing but angle of attack, and angle of attack is denoted here by alpha. Thus, alpha m can be given as alpha n is the vectorial mean angle, can be given as lambda plus alpha. Lambda is the stagger and alpha is the angle of attack. Thus, here I have defined angle of incidence I, deviation del, and angle of attack alpha. These three are very important parameters in cascade nomenclatures. I have considered a compressor cascades now. Here I'll explain relationship between different geometric angles, blade settings, and flow angles of a compressor cascades. Thus, I have given here a schematic of compressor cascades. I have explained on this figure different angles and blade settings. So I'll go slow here. Look, this is a compressor cascade I have told, and C is the chord and S is equal to pitch, which I have indicated here. I have also shown the chord line. So I have illustrated lambda. Lambda is the stagger angle. I have superimposed here the camber line. Now I have defined in this figure theta 1 and theta 2. Look, theta 1 is the angle between the chord line and the camber line at leading edge, and theta 2 is the angle between the camber line and the chord line at the trailing edge. So I have marked theta 1 and theta 2 here. Please note. Now, lambda plus theta 1, if you sum these two angles, will give you alpha 1 dash. Alpha 1 dash is the blade inlet angle. So this is alpha 1 dash. Similarly, you can get alpha 2 dash, which is the blade exit angle I have indicated here. Alpha 1 is the flow angle. So now I is the incidence. Incidence is the angle between the camber line and the inlet flow. Thus, alpha 1 dash plus I is equal to alpha 1. What I like to say, alpha 1 dash blade angle plus angle of incidence is equal to the flow angle. Similarly, I have defined here deviation. Deviation is the angle between the camber line and the exit flow. And thus I have defined alpha 2. Look, this is the alpha 2. So this is a picture, this is a schematic where you can appreciate the relationships of blade setting, different geometric angle along with the flow angles. To summarize, I have indicated here lambda, which is the stagger, which is the angle between the chord line and the axial directions. Theta, theta 1 and theta 2, alpha 1 dash and alpha 2 dash, angle of incidence and also angle of deviation, del, and then alpha 1 and alpha 2, along with the chord. This is chord that you know, and this is pitch. What I have stated earlier, I have explained further, where lambda be the stagger angle for a compressor cascades. So I continue the discussion on compressor cascades. And here is the figure that I had presented earlier. With respect to lambda and theta, the camber angle, I can now define blade inlet angle alpha 1 dash and blade outlet angle alpha 2 dash. This blade inlet and outlet angle are the geometric parameter, and alpha 1 dash can be given by lambda plus theta 1, while alpha 2 dash equal to lambda minus theta 2. So alpha 1 dash minus alpha 2 dash would be equal to theta 1 plus theta 2 equal to theta is the camber angle. Now you know for a circular arc profile, theta 1 is equal to theta 2 is equal to theta by 2. Now, ear inlet angle alpha 1 can be given by alpha 1 dash plus I, and ear outlet angle is equal to alpha 2 dash plus del, where I is the incidence and del be the deviation. Now alpha 1 and alpha 2 dash, these two are the flow angle. Now I'll define a very important quantity which is called deflection, right? Deflection is equal to alpha 1 minus alpha 2. It's actually says the deflection of fluid as it passes through the cascade, and thus the quantity deflection is related to the lift generated on the blade. Thus deflection can be stated as alpha 1 dash plus I minus alpha 2 dash plus del. So deflection would be equal to alpha 1 dash minus alpha 2 dash plus I minus del. That can be stated as theta plus I minus del. So I have given an expression of deflection which can be related to the lift with respect to theta. Theta is the geometric parameter, and I and del depends on the flow conditions, incidence and deviation of flow. Further, stagger can be related with the blade angle. Thus, for a circular arc camber line, here the stagger can be expressed as lambda equal to alpha 1 dash plus alpha 2 dash divided by 2. Cascade with parabolic arc profile, we can express lambda as lambda plus tan inverse 4b divided by 4a minus c is equal to alpha 1 dash, and lambda minus tan inverse 4b divided by 4a minus c is equal to alpha 2 dash, where a is the distance from the leading edge for maximum camber and b is the maximum displacement of camber line from the chord line. A and b I had already defined. Let me discuss about the turbine cascade now, where orientation of the blade is different than that of compressor. Here I have given a schematic and I have illustrated different angles with the blade setting. So this is the chord line, okay, and lambda is the angle that chord line makes with the axial direction. So lambda is the stagger, and I have indicated also the camber. This is the camber which have been shown by a dotted line, and theta 1 is the angle that the camber makes with the chord line at the leading edge. Similarly, theta 2 has also been shown at the trailing edge, which is the angle between the camber and the chord line at the trailing edge. And look, this is also lambda at the trailing edge. Okay. The incidence is the angle between C1 inlet velocity and the camber line. So one can evaluate alpha 1 for the turbine cascade and similarly alpha 2 for the turbine cascades, where del is the deviation which has been marked here. Here deviation is the angle between C2, this is the C2. C2 and camber line. So as I have shown you different angles related to compressor cascade, from this figure one can establish the similar correlation for turbine cascades, and it is worthwhile to note that orientation for the turbine cascade is different than the compressor cascades. Here I have mentioned about aerofoil nomenclature in brief. There are two systems. One is British practice, and while the other one is American practice. In British practice, aerofoil profile is termed as C series, while in American practice it is termed as NACA series of aerofoil. As an example, in British practice, an aerofoil is designated as 12 C4 stroke 35 P30. What does it mean? C4 stands for a particular class of aerofoil. 12 means 12% thickness. P is the parabolic profile. Similarly, NACA 65 is a series of aerofoil in American practice, so that there are books of aerofoil. So like NACA 65, you can go to the particular page where the characteristics has been stated in tables. Thus, a wide range of aerofoils have been tested and they are tabulated, and their characteristics have been tabulated. Now I have reviewed some results, particularly regarding lift and drag coefficient. For incompressible flow, we may define CL is the lift coefficient as L divided by half rho Cm squared into C, where Cm is the vectorial mean velocity and C is the chord. Similarly, CD is equal to D by half rho Cm squared into C, and zeta is equal to del P0 by half rho Cm squared, where zeta is the stagnation pressure loss coefficient and del P0 equal to P01 minus P02, which I have stated earlier as omega tilde. Now, CD can be expressed as, S by C zeta into cos alpha m. We have proved earlier. And thus for a compressor cascade, I can say CL is equal to twice S by C tan alpha 1 minus tan alpha 2 into cos alpha m minus CD into tan alpha m. This also has been proved. Now, in nominal range of applications, CD by CL ratio, this ratio, CD by CL ratio is small, much small than unity, and thus we can approximate further stating that L by D is equal to CL by CD, that is equal to 2 by zeta into tan alpha 1 minus tan alpha 2. Thus actually I have neglected this part. For low value of CD over CL, which occur in the nominal range of operation. Similarly, for a turbine cascade, I have proved that CL is equal to twice S by C tan alpha 2 minus tan alpha 1 cos alpha m plus CD into tan alpha m, while CD by CL ratio is much smaller than unity. I can neglect the contribution of CD into tan alpha m, and I can express as CL by CD ratio is equal to twice divided by zeta into tan alpha 2 minus tan alpha 1. I'll explain here the compressor cascade performance. With respect to this, I must refer the work of Hall 1942. He measured the compressor cascade performance in a low speed wind tunnel, and the test result I have presented here. He expressed the total pressure loss as zeta. Zeta is equal to del P0 by half rho C1 square. Further, he has measured deflection epsilon and also the angle of incidence I. He expressed his test result in terms of I. So x-axis is I, angle of incidence, and the y-axis, left hand side, is the deflection epsilon, and the right hand side he has expressed the total pressure loss coefficient. Now I have already explained the deviation is proportional to the lift generated on the blade, because deviation decides turning of flow within the cascade. Now suppose as we increase the angle of incidence from minus 20 degree, then note that pressure loss coefficient decreases while deflection increases. At some point, when pressure loss becomes minimum, and after that pressure loss tends to increase. Now look, even if we go beyond the minimum pressure loss, then also deflection tends to increase, but at a certain point it becomes maximum, then tend to decrease. Where it becomes maximum, that's called the stall condition. That is, when it tends to decrease, that means lift also tends to fall. It indicates that blade had already stalled, that is, the separations particularly from suction surface appeared. The point where the deflection maximum, that the stalling point, is denoted by epsilon s. And look here, the losses is almost twice of the minimum loss. After that stall point, losses tends to increase significantly with decrease of lift or deflection. So I have defined the stall point, and another point I like to define here, which is called nominal condition epsilon star, which is defined as 0.8 of epsilon s. Suppose it is here. This is called nominal condition. At this condition, a cascade is designed so that we can get some reasonable operating range. Thus, I have explained here the stall point is arbitrarily defined as the incidence I at which the total pressure loss coefficient would be twice of the minimum total pressure loss. Further, the deflection at the stall point is denoted as epsilon s, and the nominal condition is referred as 0.8 of epsilon s, at which a cascade would be designed. Now I'd like to refer to you the cascade losses. Now I'll initiate with secondary flow loss. Here I have shown a classical picture of secondary flow loss, particularly formation of horseshoe vortices. Now the boundary layer, because of viscous flow, the boundary layer will develop not only on the cascade surface, the blade surface, but also on the hub and casing. Now this boundary layer developing on the hub or the casing is referred as end-wall boundary layer in case of cascade flows. Now I have indicated here this end-wall boundary layer forming on the surface. Now turning of this incoming boundary layer within the blade passage would develop horseshoe vortices. This horseshoe vortices is a source of secondary flow loss. Thus, the losses can be classified as one is the profile loss. Profile loss is the source of formation of boundary layer on the blade surface, and this can be assessed from cascade test. So profile loss is designated at CDP. The second one is the annulus loss. The boundary layer will form on the annulus wall, and because of the formation of boundary layer on the annulus wall, there will be some loss, and this is designated as CDA, and CDA is well correlated with a relation as 0.2s divided by h, where s is the pitch and h is the height of the blade. Thus, we can assess CDA, annulus loss. And the other one is the secondary flow loss. This is because of formation of secondary vortices, as I have explained earlier, within the blade passage because of end-wall boundary layer. And this secondary flow loss can be correlated as 0.018 into CL. So I can assess CDP, that is profile loss coefficient, from cascade test, annulus loss coefficient, and secondary flow loss coefficient from some correlation. After that, I can assess the total loss coefficient as CD equal to CDP plus CDA plus CDS. Thank you for listening.